Hey everyone, and welcome back to The Future is Whatever We Talk About This Week. I'm Mark.
And I'm Jenny. And this week, Mark, I feel like we're wading into some properly times weird times territory, but also potentially really exciting. We're talking about the future of computing is noise.
Oh man, this is the cool part. Seriously, when I first started digging into this, my brain just went, ooh. We're so used to thinking about computers as these perfectly precise, deterministic machines, right? Zeros and ones, perfectly controlled.
Exactly. Every calculation has a single, predictable outcome, like 2 plus 2 is always 4. No surprises.
Right. But what if we stopped fighting the inherent randomness in the universe and started using it?
Okay, wait, let me get this straight. So instead of attempting to minimize noise and uncertainty, we're making it part of the computation?
Pretty much. So basically, what's happening with this probabilistic computing paradigm is they're leveraging things like thermal noise, the natural jiggling around of atoms, to create something called probabilistic bits, or p-bits.
P-bits? Like the opposite of a stable bit?
Kind of, yeah. Instead of being a solid 0 or a solid 1, a p-bit fluctuates between those states probabilistically. Think of it like a coin that's constantly flipping itself. But the probability of it being heads or tails at any given microsecond can be influenced.
Okay, that's fascinating. But how does that actually times compute times anything? How does a flipping coin solve a math problem?
This is where it gets interesting. One key application is in what they call thermodynamic computing. These systems can be configured to naturally settle into states that represent solutions to complex optimization problems. Kind of like how a physical system finds its lowest energy state.
You know what this reminds me of? Those marbles in a tray that naturally find the lowest points.
Exactly. It's that kind of principle, but at a nanoscale, using these noisy p-bits. And the power efficiency implications are substantial. We're talking potentially significant improvements compared to traditional GPUs.
I saw something about potentially 100 million times more energy efficient than some current GPUs? Is that realistic data?
So those specific figures, the really high ones, are often quoted from simulations and early work. Companies like Extropic are prominent in this space. And those figures come from their projections. It's a projection based on how these systems should behave thermodynamically for certain problems, compared to the energy overhead of moving data around a traditional deterministic chip. It's still early days for real-world validation.
Okay, so simulation versus real-world verified data. Still, even a fraction of that would be a big deal.
Oh, certainly. And the core idea is sound. They're targeting problems that are truly hard for normal computers, like NP-class problems.
NP-class problems. The ones where finding a solution is easy, but finding the times best time solution is incredibly difficult?
Spot on. Things like optimizing logistics, drug discovery, financial modeling. Problems where you have this vast number of potential solutions, and exploring all of them deterministically takes forever, or uses an impractical amount of energy. Probabilistic computing can explore this vast solution space more efficiently by essentially jumping between possibilities based on probability.
So, like a smart guesser instead of a meticulous checklist checker?
Yeah, kind of. And the hardware is interesting too. They're using technologies like magnetic tunnel junctions. The good news here is these materials are often compatible with existing semiconductor manufacturing processes, unlike, say, quantum computers that need extreme cold.
Okay, that's a key point. So this isn't something that requires building a whole new, wildly different factory?
That's the goal. Integrating these p-bits onto silicon wafers alongside traditional CMOS logic is a major area of research. It would allow for hybrid architectures, where the p-bits handle the parts of the problem they're good at, and the classical logic handles the rest.
That seems much more practical for near-term adoption. I can already hear our listeners thinking, how does this compare to quantum computing, though?
That's the big question, right? And it's not an either-or situation. Quantum computers offer the potential for solving certain problems, like breaking high-level encryption, that neither classical nor probabilistic computers can handle efficiently. They leverage superposition and entanglement. And they require those incredibly cold temperatures and delicate setups.
Right, and they require those incredibly cold temperatures and delicate setups.
Precisely. Probabilistic computing is aiming for a different sweet spot. It's trying to get some of those energy advantages for optimization and AMI tasks, but using hardware that's closer to what we already know how to make it scale and operate at room temperature.
It sounds like probabilistic computing might be something we see integrated into devices and data centers much sooner than widespread, powerful quantum computers.
That's a distinct possibility. The semiconductor compatibility is a notable advantage in the near term. We could see hybrid chips showing up to accelerate AI training or tackle specific optimization challenges much faster.
Beyond the energy angle, are there other big implications? I saw something about encryption.
Yeah, that's a fascinating tangent. Some research suggests probabilistic systems using Boltzmann machines could potentially tackle certain factorization problems that are core to public key cryptography more efficiently than is possible with traditional computers. We're not talking breaking the internet tomorrow, but it's prompting a look at post-quantum cryptography considerations from a different angle.
Okay, so even the noise has security implications. This is interesting. So what are the big hurdles then, besides getting those initial efficiency numbers verified in the real world?
Scalability is a big one. Getting individual p-bits to work is one thing. Building massive, interconnected arrays that don't lose their useful probabilistic properties at scale is another. Reliability in all conditions is also something being actively researched. If you're relying on thermal fluctuations, how do you ensure consistent behavior across a wide range of environments for critical tasks?
Right, you wouldn't want your self-driving car to have a moment of, probabilistic doubt at a critical moment because of a temperature change, for example.
Precisely. So, engineering systems that embrace that noise while still being robust enough for real-world applications is essential. But the potential is significant, especially for integrating with AI systems to handle complex, uncertain, real-time data.
Okay, so let's talk about that. What are the potential downsides? Are there negative consequences to relying on noisy computation for certain critical tasks? I mean, you mentioned self-driving cars. That needs to be reliable, right?
That's a major concern, and a valid criticism. Noisy systems, by their nature, could be prone to unpredictability. While that's useful for exploring many solutions, for safety-critical applications like medical diagnostics or autonomous vehicles, that unpredictability could be problematic.
Yeah, you can't have a diagnosis that's probably right, or a car that might stop.
Exactly. The error rates due to natural noise might exceed acceptable thresholds for fields requiring outcomes you can count on. Your research is looking at ways to manage and bound that randomness.
So it might be better suited for problems where a less than perfect solution is acceptable, or where you can run the computation multiple times to increase confidence?
That's likely where we'll see the initial impact. Problems like optimizing large logistics networks, where a small deviation isn't catastrophic. Or in certain AI tasks, where the probabilistic nature can help explore richer solution spaces for things like image recognition or natural language processing.
Okay, that makes sense. So maybe not powering the brakes on your car initially, but improving the traffic flow calculations for the city?
A fine analogy, Jenny. The applications will likely align with the strengths of the technology.
All right, before we wrap up, let's get some listener thoughts. We asked on social media, would you trust an AI-driven decision made by a computer using noise rather than traditional logic? We got some interesting responses.
Oh, I can imagine. It feels counterintuitive, doesn't it? Trusting something based on randomness.
One listener, Sarah, said, definitely not for surgery or flying a plane. Maybe for recommending movies? Which feels like a practical line drawn there.
Yeah, that seems like a reasonable approach initially. Start with low-stakes applications.
And Tom said, as long as the engineers can explain why, it made the decision using the noise maybe. Explainability is key, which ties into the reliability point we were just discussing.
That's a good point, Tom. Understanding why a probabilistic system settled on a certain solution is another area of active research. It's not as simple as tracing a deterministic calculation.
Okay, so the key hurdles seem to be real-world verification of those simulation projections, scalability while maintaining those useful properties, and building in reliability and explainability for critical tasks. But the potential energy savings and ability to tackle difficult optimization problems are truly compelling.
Indeed. It's a different approach, leveraging the inherent physics of the universe instead of trying to force it into rigid, deterministic boxes. It takes some getting used to, but it's certainly a promising direction.
So is the future of computing actually noisy?
In a way, yeah. It's about embracing the inherent randomness and using it as a resource rather than trying to eliminate it.
That's a complete mindset shift from how most of us think about computers.
It completely is. And that's why it's so exciting. It's a fundamentally different way of approaching computation, and it could open up doors to solving problems we can't efficiently tackle right now, all while using times less power for certain tasks.
Well, consider me intrigued. The future of computing is noise. Who knew? Thanks, Mark. That was illuminating.
Anytime, Jenny. Always happy to dive into the weird and wonderful world of future tech. And thanks for the great questions and insights, as always.
And thanks to all of you for listening and participating in the polls. We'll catch you next time on The Future Is.